Hello everyone and welcome to Robot Operating System version 2 Jazzy Jalisco, or briefly ROS2 Jazzy Jalisco tutorials. In this tutorial we are going to explain how to write from scratch a ROS2 package and a C++ program that will set and publish joint states. More precisely, the C++ program will define and publish joint states, and these joint states will be sent to the RViz simulation that will animate the robot motion, and the robot motion is shown over here. Here, for the presentation clarity and brevity of this video tutorial, we have created a robot model consisting of 3 links: the first base link, the second link, and the third link over here. In addition to these 3 links, we have 2 joints. Here's the first rotational or revolute joint, and the second joint is over here. It's a translational or prismatic joint. Here's the C++ code. This C++ code embeds the joint state publisher node inside of a C++ class and defines several important functions as well as objects. More precisely, this C++ code will, inside of this function, define a robot state. That is, it will define the state of every joint of the robot, and then it will move the robot according to a simple law. The law is defined over here. Over here, we are simply going to rotate the first joint until we reach the limits, then we'll go back, and the same thing will happen for the prismatic joint. We will simply move the prismatic joints until the end of the limits, and then we will go back. And we are doing this periodically. And as the result, you can see this animation over here. It's really nice. Although this is a simplified robot model, everything explained in this video tutorial can be straightforwardly applied to more complex robot geometries. In addition to this video tutorial, we have created this detailed manual and instructions explaining how to implement everything from scratch. This manual contains 8 pages and thoroughly explains everything. This manual, as well as all the files, including the C++, Python, Launch, configuration files, and the complete build package, will be provided in the description below. That is, links to all the files will be provided in the description below. Okay, let's start this video tutorial with a brief summary of everything that you will learn in this video tutorial. In this ROS2 Jazzy tutorial, we explain: number 1, the basics of ROS2 joint state and robot state publishers and how they fit into the big picture of controlling robot models. Number 2, how to publish joint states from a C++ code file in ROS2 Jazzy and how to use the published joint states to move the robot RViz simulation. Number 3, how to create a minimal unified robot description format or URDF file format and a model for modeling the geometry of a robot. Number 4, how to create a ROS2 Jazzy package and launch files for visualizing the URDF model. And number 5, how to visualize and simulate the robot geometry and motion in RViz and ROS2 Jazzy Jalisco. Some of you are completely new to ROS2 as well as to robotics, and let's briefly explain these terms. First of all, URDF file format is a widely used XML file format for describing the geometry and configuration of robots. It's used in ROS and Gazebo to define the geometry, joints, and configuration of robots. On the other hand, RViz is a 3D visualization tool, and way more than that for ROS2. Launch files are ROS2 files that are used to configure and run at the same time a number of ROS2 nodes and other components of a ROS2 system. For example, with a single launch file, you can run a number of different nodes and components for controlling a mobile robot. Here's the license and the copyright notice. This document, develop code files, lesson video, and all the provided material are referred to as the learning material in the sequel. Number 1, the learning material is the ownership and the original work of Dr. Alexander Haber, who is referred to as the author in the sequel. You have the right to use the learning material for personal educational use and strictly for non-commercial use. The learning material should not be copied, redistributed, or publicly posted on public or private websites, code repositories, and social media platforms. The learning material should not be reproduced manually or automatically using an algorithm or an AI model from this video and then posted on public or private online repositories. Unless allowed by the author, the learning material should not be used as lecture material on online learning platforms and in official or unofficial university courses. Unless allowed by the author, the learning material should not be used to train engineers working in companies or paid academic researchers, such as paid students, paid postdocs, paid professors, etc. Then number 7, the provided code files and learning material should not be used to train an AI algorithm or a large language model. And 8, unless allowed by the author, the learning material should not be used to produce academic papers, student reports, or other documents, or any graph or any piece of code presented here should not be used to produce papers, reports, or other documents without explicit approval of the author. Okay, let's start with implementation. First of all, open a terminal. You can do it like this. Click here and search for terminal. And then over here, I'm going to resize the terminal. And let's start with the prerequisites. To implement the material presented in this tutorial, you need to have Linux Ubuntu 24.04. Do not use Windows Subsystem for Linux or WSL since you might have issues displaying graphics. Install Linux Ubuntu on a computer. If you have a Windows computer, then you can install Linux Ubuntu in parallel to the Windows operating system by using dual boot approach. Let's verify that you have the correct Linux Ubuntu version. To do that, type this, and you should see over here Ubuntu 24.04. This third number really doesn't matter. Next, we need to verify that you have ROS2 Jazzy Jalisco installed on your computer. To do that, simply type this command, and if ROS2 Jazzy Jalisco is installed, this command will list the content of the installation folder. In my case, since ROS2 Jazzy Jalisco is installed, this folder is not empty. Next, let's verify the installation by trying to run this setup script from this folder. And if you don't see any error, this is good. This means that ROS2 Jazzy is most likely installed, and to finally verify the installation, simply type this, and this should print the ROS2 Jazzy distribution. If you see Jazzy, it is okay and you can proceed further. On the other hand, if you don't have ROS2 Jazzy Jalisco installed on your system, then go to my channel and you will find a video explaining how to install it. Okay, next, let's start with important definitions and some background information that will help you to properly understand the steps that we are performing in this video tutorial. This graph over here shows the communication structure and all the nodes that are used to generate the simulation that you saw at the beginning of this video tutorial. Namely, over here we have 1, 2, 3 nodes, as well as some other nodes that are not displayed over here. This first ellipse over here represents the joint state publisher node. This is the node we implemented in our C++ program. This node will set all the joint states, that is, it will define the state of the revolute joint, that is the rotational joint, and the translational joint. Then it's going to publish these states through this topic joint states. Then on the other hand and on the other side of this topic, we have the robot state publisher node. This is the standard ROS2 Jazzy robot state publisher. The purpose of this node is to receive the joint states and to use the URDF model and create the forward kinematics model, and then to publish the robot pose through the TF topic, and this TF topic sends robot pose in with all the degrees of freedom properly defined and all the relation between the coordinate system properly defined to RViz, that is to this transform listener node, and this transform listener node is used to display, and RViz of course are used to display the robot motion in RViz simulation environment. Okay, this is very important to understand. But wait a second, what is the state of a joint? Let's properly define it. In ROS2, the state of a joint, either revolute or prismatic, is defined by number 1, the position or the angle of rotation of that joint. In the case of revolute joints, the component of the state is the angle of rotation expressed in radians. On the other hand, in the case of prismatic joints or translational joints, the state is the position of the joint expressed in meters. Then number 2, the linear or angular velocity of the joint. In the case of revolute joints, the component of the state is the angular velocity expressed in radians per second. On the other hand, in the case of prismatic or translational joints, the component of the state is the linear velocity expressed in meters per second, or briefly m over s. And the third component of the state is the force or torque. Both are referred to as the effort that is applied to the joint. In the case of revolute joints, the component of the state is the applied torque expressed in Newton meters. In the case of prismatic joints, the component of the state is applied force to the joint expressed in newtons. Note that this definition of the state is different from the kinematic state definition, which only takes into account the positions, that is angle of rotation, and velocity, that is angular velocity. For example, when you write a state space model in control theory, the states are kinematic states. However, the forces are considered as input. And this is a very important difference between everything what you learn in control engineering class and ROS. In ROS2, the state is position, velocity, and force. Or in the case of angular joints or revolute joints, it is angle of rotation, angular velocity, and torque. On the other hand, if you open a control engineering textbook, the state is only the position and velocity, or in the case of revolute joints, the state is angle of rotation and angular velocity. Forces in control theory are considered as inputs. In our C++ code, we implemented the node called joint state publisher. You will see that implementation later on. This node publishes user-defined states which are used to move the robot simulation. The state is communicated, or better to say published or received, by using the topic called joint states. And this topic is the standard topic in the ROS2 Jazzy world. Keep in mind, don't change and don't use the name of this topic for something else. The state information is received by the node called robot state publisher, and this is the standard ROS2 node. This node receives the state information for every joint, and by using the URDF model of the robot, publishes 3D poses of the robot links using a kinematic tree of the robot. On the other hand, the node robot state publisher makes use of the URDF robot description defined by the parameter robot description, and you will see that parameter later on. Here, it might be a good idea to, at the point when we explain the C++ code, to go back here and again to listen and watch this part of the video tutorial. What is very important to keep in mind that robot state publisher publishes or receives, or let's correct ourselves, receives joint states through this topic, joint states, and calculates forward kinematics of the robot and publishes the results to the TF2 topic. That is, the state of the robot is published to TF topic. TF2 is a transform library that is used to keep track of the relationship between coordinate frames over time. It maintains a tree structure describing the relationship between the coordinate system as well as the links and joints. Now that we understand what needs to be implemented in this video tutorial and what are joint states, let's start with implementation. First of all, you have to make sure that you're in a terminal where you sourced the environment. This is very, very important. And I'm going to do it here once again to show you what you need to do every time when you want to play with ROS. So open a terminal, and the first step when you want to create a package is to source the environment. Sourcing the environment means that you are executing this setup.bash file from this installation folder. So let's run this, and now the environment is properly configured. The next step is to install the necessary packages. Most likely, if you installed ROS2 Jazzy Jalisco by using the standard way. That is, if you install the full ROS2 Jazzy Jalisco desktop version, then you have all the packages. However, it's still a good idea to try to install the packages. First of all, we will need the robot state publisher package, and we install it like this. Enter your username and then install the RViz package. And that's it. Now, before I continue, it's still a good idea to verify that you have all the packages on your system. To do that, you need to run this command. This command will list all the packages that you have on your system, and you can see the packages. There are probably hundreds of packages, and this is not the most optimal way for searching for a particular package. To do that, that is to search in a more optimal way for a particular package, you need to use this command. You call ROS2 package list, and then you filter results by using grep, and over here I'm going to display every package that contains the word joint, and you can see what are the packages: joint limits, joint state publisher, and joint state publisher GUI, and RQT joint trajectory controller. In my case, the most important package is joint state publisher. Okay, you can do the same thing for RViz. You can simply type this. Oops, I made an error. And you should see over here RViz. Good. The next step is to create the package, URDF, launch files, and C++ files. So let's do that. Here we are in the terminal where we sourced the environment. However, it's still a good idea to try to do it once more, just in case. Then go back to the home folder if you're not in the home folder. And over here, let's create two folders. You're going to do it like this. This command creates a folder called demo_workspace, and this is our base or the workspace folder. Inside of that folder, we have created a source folder. This is the folder that will contain the source files of our package. Consequently, navigate to the source folder. The next step is to create an empty package. When I say create an empty package, this means to create all the files necessary to build the package. Namely, here we are going to use a version of CMake, and to use CMake we need to create a certain number of files and folders. To do that, we need to execute this command. However, keep in mind that this command should be executed inside of the source folder. And let's explain what this command is doing. We are calling ROS2 package create. This is the command. Then we are specifying the build type. The build type is embed CMake. This means that we are using CMake, and here's the name of the package. I will call the package as demo robot, and let's press enter over here, and this will create the package. Now if you type this command inside of the source folder, you will see another folder which contains the source files of our package. So let's navigate to this folder and let's see its structure. Here you see several important files. First of all, this is the CMake configuration file that we will have to modify later on. Then you see this folder include. Currently it's an empty folder, and this folder can include header files or any files that will be used in our code. Then over here we have another configuration file of our package, package.xml. We will modify that file later on. And over here we have another folder. This is the default source folder containing the source C++ or Python code. And this is the basic structure of our package. However, we need to create additional files and folders. First of all, let's start with folders. This command will create 3 additional folders. It's going to create a folder called launch, then it's going to create a folder called URDF, and finally it's going to create the folder called config. Let's create these folders and let's explain their purpose. Let's start with launch. The launch folder will contain the Python launch file. This file will be used to start the necessary nodes in our simulation. Then Config folder will be used to store the RViz configuration file, and then the URDF folder will be used to store the URDF description of the robot geometry and joints. The next step is to create the URDF file of our robot. For that purpose, navigate to the URDF folder, and inside of this folder you need to create the file. In my case, I'm going to use Visual Studio Code to create the file. However, you can use any other editor. To start Visual Studio Code, I need to type this. Most likely you don't have Visual Studio Code on your system, and if you want to learn how to install it on a Linux Ubuntu, then go to my channel and find a YouTube tutorial on that. Simply search VS Code Linux Ubuntu and you will find the tutorial. And here it is. Next, I need to create the file. Over here, you need to be very careful about the file name. I'm going to call the file as model.urdf. So let's create such a file. Click on File, a new file, and call it as model.urdf. Make sure that you don't make any spelling error. And save it in the URDF folder. Here it is. And here, to save time, I'm going to simply copy and paste the content of the file. So here's the file. To understand this file, we need to first of all understand the geometry of the robot. Over here, I created a 2D representation or a sketch of our robot. So here it is. The robot consists of 3 links. We have the base link, we have the first link, and we have the second link. Those of you who are not familiar with the URDF, in the URDF description, robot geometry is modeled by using links. Between the links, we have joints. Between the base link and the first link, we have joint 1. It's a revolute joint that can rotate around the vertical z-axis. And we have joint 2, which is a prismatic joint, and this joint is used to provide a translational motion between second link and the first link, and we need to implement this geometry. So let's start immediately. Okay, so let's go back to the Visual Studio Code and let's explain what is written over here. First of all, whenever you start a URDF file, you need to enter this line. Then this is how we write comments. We start the comment like this and we end the comment like this. We can simply erase this line since it really doesn't matter. However, this line is instructional in order to explain how comments are being written. Then we start the URDF file robot description with this tag robot, and then at the end of the file we need to close a robot. This is very, very important. Whenever you open a tag, you need to close it. This is the first way of opening and closing tags, by using multiple lines. However, there is another way. You can open it and close it in a single line, and we will learn that later on. Here you need to specify the robot name. I will call it as simple robot. Then we need to define our first link. We start the link tag and we end the link tag over here. And so let's go back and let's see what this link is. Its name is base link. Okay, so we call it simply as base link. And over here we define the visual representation of the link. Here we need to define the geometry. Geometry is a cylinder. Here you can see the 2D projection. Width, let's see, what do we have? Radius is 0.3. Here you can see the diameter, and the height is 0.1. And that's precisely what's being specified over here. Note that the height is denoted by length. Then we need to set the origin, or better to say the origin of the coordinate system associated with this link. This coordinate system origin is defined with respect to some other coordinate system that's not being specified over here. However, you can think of that coordinate system as the world coordinate system. And this origin contains several parameters. First of all, x, y, z represent the translation of the origin with respect to the origin of the world coordinate frame or coordinate system. And these angles RPY represent roll, pitch, and yaw Euler angles, which tells you how the coordinate system axes are being rotated with respect to the base or the world coordinate coordinate system. Here I need to be precise and say Euler angles that define rotation of the frames of this coordinate system with respect to the axis of the coordinate system associated with the world or some fixed coordinate system. Then we need to specify material name, and over here we need to specify the code for the color, and we end the material, and we end the visual. Now, remember that I said that tags can start and end in a single line, and here's one example. If you start a cylinder tag like this, you can end in a single line like that. Okay, the next step is to define the first joint, and here's the definition. So let's look at the graphical representation of the joint. Here it is. It's being displaced for 0.05 with respect to C1. However, C1 is actually the world coordinate system. And when you define this coordinate, better to say the coordinate frame of joint 1, you need to define it with respect to the world coordinate system. And this is a mistake that people often do. They think that this joint coordinate system, or the coordinate system of joint 1, is defined with respect to the center of the first link, and this is not the case. So let's define it properly. First of all, the name is joint 1. The type is revolute. Revolute means rotational joint. Then we need to specify the parent link. The parent link is what? In our case, the parent link is the base link, and the child link is the first link. That is link over here. Then we need to specify the position of the origin of the coordinate system associated with joint 1 and the orientation in Euler angles. Over here, we don't have any rotations. However, we have the displacement in the direction of the z-axis, and this displacement is 0.05, as you can see it over here. Then we need to specify the limits. Here the limit effort means that the maximum torque that can be applied to this joint is 300 Newton meters. Then we need to specify the max velocity is 2. Then we need to specify lower and upper rotational limits. They are expressed in radians. Here, minus 1.57 radians is approximately minus, I think, yeah, this is pi over let's see, pi over 2 and plus pi over 2 or something like that. This really doesn't matter. Okay, then we need to specify the first link. Okay, the link name is first link. Then we define the visual representation. It is defined as a cylinder with a length of 0.5 and the radius, let's see what is the radius over here. It should be properly defined. It's 0.08, and that's precisely what you see over here. And then we need to specify the position of the origin of the coordinate system of this link with respect to the position of the coordinate system of joint 1. And over here we can see that displacement is 0.25 in the z-axis, and consequently you have it over here, and we don't have Euler angles over here. Next we specify the color, and we end the visual. Next we need to define second joint. We call it as joint 2. It's located over here. Then the type is prismatic. The parent link is the first link. Here it is. The child link is the second link. Here's the second link. And then over here we need to specify the center of this link. Here it is. Or actually this is not the center. This is how much is joint 2 coordinate system displaced with respect to the coordinate system of joint 1. We have an offset of 0.5, and that's precisely what's written over here, and we don't have Euler angles. And over here we need to specify the axis of rotation. Here we are going to, not rotation, here again I have to be very precise. This is the axis of translation, and this axis is the y-axis. That is, this link can move along the y-axis, and we specified 0, 1, 0. Then we specify the limit effort. This joint can accept up to 300 newtons of force. The velocity is 2. The lower limits and upper limits are -1 and 1. And finally, we need to define the second link, that is this link over here. Geometry is a box. These are the dimensions, 0 0.2, 2 and 0 0.1, 0 0.1. Here, I kind of changed a little bit the dimensions. This is, here it's written 0 0.7. However, the dimension here is 2. That is, in simulation is 2. However, on this graph is 0 0.7. I will correct it later on. And over here, the third dimension is 0 0.1. Okay, and that's the geometry. Next, we need to specify the center of this link and the associated coordinate system. Here it is. It's only being displayed 0.05 with respect to the join to coordinate frame. And then we need to specify material. We end the material, we end the visual, we end the link, and we end the robot. Simple as that. And here again is the file, line 1 to 29, and then from line 29 to the end. Here it is. Good. Next, let's save this file by pressing Ctrl S. The next step is to create the launch file. The launch file should be actually created in this folder. The name of the folder is launch. So I will just navigate to this folder to show, oops, I made an error. I will navigate to this folder to show you the path of this folder. So here it is. And again, I'm going to use Visual Studio Code to create the launch file. To create the launch file, I need to first of all name it properly. And over here, I need to follow a convention. Usually the convention is display.launch.py. So basically the file should have .launch.py. However, you can use any other name. Okay, so let's create an empty file. File, new file, and let's call it display.launch.py. Here it is, display.launch.py, and let's save it in the appropriate folder. Go to the package folder, go to launch and save it over here. And again, to save time, I'm going to simply copy and paste the content of the file that I wrote previously. But before we start with the explanation, let's explain what is the purpose of this file. The purpose of this file is to compress and to ease our life when starting ROS2 nodes. Namely, we are going to create and start several nodes by just executing this Python file, and that's the purpose. So let's understand what is written over here. First of all, we need to import the necessary libraries. We need to import launch, and from launch substitutions, we need to import command and launch configuration, and then we need to import launch ROS, and we need to import ROS. Over here, we need to specify the package name. Here, the package name should be precisely the name of the package that you used when creating the package. Then we need to specify the relative path of the URDF file with respect to the package path. So what is the package path? Well, if I go back to the terminal, this is the package folder, right? And the URDF file is defined in the URDF folder and then the name of the file, and that's precisely what is written over here. Then I need to specify the relative path of the RViz configuration file. We still didn't create the RViz configuration file, however, we can still specify it over here with no problems. So this file is placed in the config folder, and the name of the file should be config.rviz. This function over here is used to define and launch nodes. First of all, we need to create, or better to say, to retrieve the absolute model path. That is the absolute path of our URDF file. Here, with this line, we can retrieve the package path, and that's why we are basically using OS and these launch substitutions, since these functions will enable us to automatically retrieve package path. Okay, then we are specifying over here the absolute URDF model path. We are simply joining two paths, the relative path and this absolute path of our package, and we do the same for the RViz configuration file. And over here, we are just printing to double check the URDF model file path in order to make sure that everything is correct. The next step is to load the robot description. That is, over here we are loading the URDF file of the robot. With open, and then we are specifying the absolute path to the URDF model file, and then we are simply storing the complete description inside the robot desk. Then we define this dictionary called parameters, and we are passing, or better to say, inside of that dictionary we are specifying robot description, and then we are passing this complete robot description, which is nothing less than a big string. Then we need to define and later on create the robot state publisher node. So we are calling it as robot state publisher node. Then we are using the function launch ROS.actions.node, and then we specify the package name, we're specifying the executable, where do we want to show the results on the screen, then we specify parameters, and we specify the arguments. As parameters, we are passing this dictionary, and as the arguments, we are specifying the absolute path to the URDF file. Note over here that this package is the standard ROS2 package. That is, we are referring to the standard ROS2 package. Then we need an additional node, and this is our RViz node, and we follow the same strategy. We are saying here that we are using the standard RViz package, we are specifying the executable, we specify the name, where do we want to print it out, and over here we are specifying the path to the configuration file. Here it is. The first time we run this code, the configuration file will be empty and nothing will be displayed correctly. Later on, once we display the first version, we are going to do several adjustments in RViz, and then we are going to save the configuration file in the appropriate folder, such that next time we launch everything will be launched with proper definitions. And then finally we combine everything and return the values. We simply return launch.launch description, robot state publisher node, and RViz node. These are the two nodes that we are starting at the same time, and consequently this file will start robot state publisher and RViz node. So let's save this file and let's continue further. Again, don't forget to save this file. The next step is to create our C++ file. To do that, we need to go to the appropriate folder. Here I'm going to use the Visual Studio Code, so it really doesn't matter where I am from the command line. However, I need to show you one important thing. All the source files, that is, all the files which are Python or C++ files, should be stored inside of this folder. So let's create the C++ file. Click on File, click on New File, and let's call the file as test.cpp. And let's save this file in the appropriate folder. It should be source, and let's save it over here. Good. Let's create the content of this file. Here, again, to save time, I'm going to simply copy and paste everything, and then I'm going to explain the content of the file line by line. Here it is. Okay, so let's explain what this file is doing. This file implements a class that embeds a ROS2 publisher node for publishing joint state and a timer object for ensuring that the publisher function is called periodically, as well as some other things. However, these are the two most important things. Now, here is one very important comment. Here, I didn't want to split this file into two files. That is, a usual practice is to define a header file, and then to define implementation file, and then finally to use these two files in third files, which will be our main file. Here, for brevity, and since this code is not complex, I compressed everything inside of a single file. However, if you want to, or if you're developing a more complex code, then consider splitting everything into several files. Okay. Whenever you write a C++ code and you want to use ROS2, you need to include the RCLCpp package, or better to say the header file. RCLCpp is the ROS2 client library for C++ that is included with any standard installation of ROS2. RCLCpp provides the standard application programming interface, or API, for using ROS2 in C++. Then we need to include the header file for joint states. Here it is. Then we need to include CMath for math functions. Then here we need to include threads. Threads are basically tasks, or better to say processes, that are being executed concurrently. Here we are not explicitly using them. However, you might in the future wish to use threads or something similar. So let's include this library. And then over here, we include the header file in order to work with time functions. And over here, we are using namespace std chrono to simplify the notation. Here's our class that defines the joint state publisher node. So whenever you want to write a ROS2 class, you need to inherit this class for some other parent class. In our case, the name of the parent class is node. And consequently, over here, we are saying that this class is actually inherited from the base class. Inheritance means that this class over here inherits all the public methods and all the private member variables from the base node class. In addition to this, this class will implement additional functionality. Okay, whenever you define a class, you need to define public member variables and functions and private member variables and functions. We start with public. Here's our constructor. What is the purpose of this constructor? The purpose of this constructor is to instantiate the objects. You will see that later on in the main function how we are implicitly calling this constructor. Now, here we need to call the constructor of the parent class, and we need to set the node name. The node name is joint state publisher, and we pass this name to the constructor of the base class. Over here, we are doing several things. Now, before I explain these 3 lines, let's go into the private member variables and let's explain what they are. First of all, over here, we are declaring a publisher object. You can see it like this, what we are doing. We are saying RCLCPP publisher, and then we are specifying the type of the message that's being published. In our case, it's the joint state. And joint state is the part of message, and message is part of sender messages. And then we are using this shared pointer, and we call the object as joint state publisher. Okay. Now, if you go to this line, that is to line 55, you can see how we instantiate it. Okay, we are saying joint state publisher, this create publisher. This create publisher is actually a function of the parent class node. Then we are specifying what type of messages we want to send. Then we are specifying the name of the topic that's used to communicate these messages, and the name of this topic is joint states. Note that the joint state topic is the standard topic used in the ROS2 world. And don't change the name of this topic, because the publisher node, or actually this robot state publisher node, receives by default information by using the joint state topic, and over here we specify the buffer size, and that's it. Then we print the message in the terminal by using this line, and then before we explain this line over here, let's explain what is a timer object. If you go to the private member variables and objects, you will see how the timer object is declared. RCLCPP timer base share pointer timer object. Timer objects has several purposes. First of all, the purpose of this object is to make sure that a certain task is being executed with a certain period. That is, when we create a timer, we are specifying the following. We are saying we want to do something with a certain period or with a certain control frequency. And this is done automatically, something like an interrupt, but not exactly an interrupt. Interrupt is something else. Interrupt will act whenever there is something coming through a topic. This is not exactly that. And we instantiate it like this. We call the createVolTimer function from the base or parent class. Then we specify the period of the timer. Here it's 100 milliseconds. And then here comes a very important part. Here we are binding or connecting this timer with this function called publish function. This function is actually a member function of our class, and over here you can see it's simply declared as a void function. And let's explain again and let's stress. So the timer object will call with a period of 100 milliseconds this function over here, and that's it. Okay, and then let's proceed further. On the line 63, we are simply saying, okay, there is a public function called publish function, okay, and then let's continue with the private member variables. We explain the publisher and the timer objects. However, over here we have doubles. They're used as constants and variables. First of all, angle is used to define the angle of rotation of the first joint, and distance is used to define the translation of the second joint. And over here I have increments for the angle and distance. Angle and the distance will increase or decrease by using this increment every period defined by the timer, and this will be defined later. Okay, and here's the implementation of the public function. So what do we do inside? This publish function will set the angle and the distance of joint 1 and joint 2, and it will simply publish these values. However, you cannot simply publish them, you need to create an appropriate message. And this is what we are doing over here. We are creating a message that will store the joint state. I'm going to call this message as joint state message. When you're creating something like this or declaring, you're actually setting a lot of values to 0. That is, they're being automatically initialized. Here we need to create and add a timestamp, since our joint state message needs to have a timestamp. So I'm calling joint state message, then I call header.stamp, and I'm getting the current CPU time. Then here we need to specify the joint names. The joint names are joint 1 and joint 2, and these are precisely the names from our URDF file. That is, the name of the joint 1 is joint 1, and the name of the joint 2 is joint 2. And that's it. Let's continue. Then we need to specify the position. Here we are calling joint state message.position, and we are specifying angle and the distance. Angle and the distance are actually initialized as zeros once everything is being created. However, later on we are going to change it over here. Now, the joint state message also contains other fields. It contains the torque or velocity, it contains the torque and the force, that's the effort, and it also contains velocity. Here we are not specifying these additional two components of the joint state, we are only playing with position. Of course, you can also specify the velocity and the applied force. Here we are simply incrementing the values, and over here we are doing the following. Every joint has its boundaries. Okay, so when we define joint 1, that is the Revolut joint, we specify these boundaries. The same thing applies for joint 2. This joint has its physical boundaries. So what do we do over here? When we reach the boundaries, we reverse the increments and we go back. That is, first we go forward, rotation or displacement. Once we reach the boundaries, we go back, and that's it. And this will create the periodic motion that you saw at the beginning of this video tutorial. You can simply change this or implement any law. For example, you can implement a law where your joint is going to spirally move or something similar. And then finally, once we update everything, we simply publish the values. That is, we publish the complete message, joint state message. And this message will be sent through the topic whose name is joint states. You can see where this topic is being defined. And this value, that is the value of joint state, will be passed further to the robot state publisher. The robot state publisher will create TFs, that is, it will create the pose and all the coordinate transformation, and it will publish it further through the TF topic to RViz, and RViz will display everything. And this will happen with a period specified by our timer object. And this period, if you go back here, is 100 milliseconds. Simple as that. So nothing special. Okay, so let's go further. Finally, we print the message in the terminal, published a joint state. And here's our int main function. Int main function is super simple. This is the standard part. Here we are actually initializing the RCL-CPP, that is, we are calling the init function. Keep in mind that before using the RCL-CPP, we must initialize it by using this command. This should be done once per process. This function will initialize any global resources that are necessary for the middleware and client libraries. Then after that, we need to instantiate a node. I call it as a test node. To do that, I'm simply calling make shared and specifying the type of the node. This is the node we just defined, and that's it. This will do the following. It will call, first of all, this constructor. Here it is. This constructor will set up everything, define all the connections, and that's it. And then finally, after we do that, we need to spin the node. The spinning of the node means that the node will start and everything will be run in the background. And then at the end, we need this shutdown function. The purpose of this function is that, for example, if a user presses Ctrl+C, you don't want to immediately exit the program. You first want to release all the resources and then you want to exit the program. And that's exactly what is happening inside of this function. And finally, we return 0. And that's it. That's our C++ implementation of the joint state publisher node. Next, make sure that you save this file, and the next step is to modify 2 additional configuration files. Let's go back to the terminal and let's go back to the package folder. If you type this command, you will notice that there is a package.xml and CMakeLists.txt file. We need to modify them. To do that, let's start with the package.xml file, go back to the editor and open it. Here it is. Over here, we need to specify and to tell to the ROS2 system that our package depends on additional files and on additional packages. And consequently, we need to write these lines. I'm going to copy these lines, and somewhere over here, you need to enter them. So what is happening over here? First of all, we are telling to ROS2 that our package depends on the standard robot state publisher package. Then we are saying that our package depends on RViz, since we are using RViz, and in addition we need to say that our package depends on the sensor messages and RCL-CPP packages, or better to say header files defining the appropriate functions. This is because in our C++ code we are using these header files. Namely, we are using, first of all, RCL-CPP and sensor messages. These are actually the packages, and consequently over here we need to say that. So let's save this file and let's continue further. Here's one side comment. In addition to these edits over here you can specify the version of your code, description, you can specify the email, and you can specify the license. Due to making this video tutorial as short as possible, I'm not going to make these edits. However, consider to make these edits in order to make your package to look more professional. Okay, the next step is to edit the CMake text file. So let's open that file, and here it is. And here you need to properly implement the following. To save time, I'm going to simply copy and paste the files, or better to say, the lines that you need. And over here are the edits. So after this find package m and CMake required, we need to add 2 additional lines. So here they are. We need to specify find package Then sensor messages required. That is, here we are saying to the CMake system to locate the sensor message package. And that's precisely the package used over here for using the joint states. Okay, similarly we need to type find package RCL CPP required. Then over here we need to create an executable file. So here's the catch. First of all, test.cpp file has to be compiled. Okay. However, in order to compile it, you need to specify the name of the output file. That is the name of the executable. And over here, I'm going to call it as test_control. This file will be executed at the end of this tutorial when we want to start our publisher node. Simply, I'm going to type ROS2 run, the name of the package, and then the name of this executable. However, you need to link to this executable to the source file, and you need to specify the relative path. Our source file is in the source folder test.cpp. Then we need to set the target dependencies. There, test control, that is the test control executable depends on sensor messages and RCL CPP. This is really, really important. Then we need to install targets. So what does it mean to install targets? Well, to install targets, we need to say that the test control at the end should be in lib and the project name. This is very important, since if you don't do that, you will not be able to run this code. And then finally, you need to tell to CMake that there are source files stored in the launch, URDF, and config. This is really, really important. You don't need to specify here the source folder, since the source folder is understood by default to contain the source files. However, you need to specify these folders. Another important thing, if you want to add additional folder, you need to type the folder name over here. So let's save this file and let's continue. The final step is to build the project. To do that, you need to go back one step down, another step down, and you need to go back to the workspace folder. However, before building the project or building everything and compiling everything, we have to make sure that all the dependencies are properly installed. To do that, first of all, run this command and enter your password. This command is going to install one very useful tool called ROS2. Then let's initialize this tool, and finally let's update it. You can simply ignore any error if you see them over here. And then finally let's verify that all the dependencies are installed by typing this. And you should get this message, all required ROS2 dependencies are installed successfully, and we can continue. Next, make sure that you are in the base workspace folder, that is in the home demo WS, and make sure that the environment is sourced. In my terminal window it is, and then we can build, or better to say compile everything by typing this colcon build. Then symlink install, packages select, and we simply need to specify the name of the package. And that's it. And let's hope that we will not see an error. Okay, no errors. This is really good. We were able to compile C++ code, and we were able to do all sorts of things behind the scenes. Good. The next step is to start the RViz simulation. Consequently, open a new terminal, and then inside of this terminal, you don't need to source the base environment. That is, you don't need to source a ROS from scratch. You can go anywhere you like, to any folder. However, you need to run this command. This command will now execute the setup.bash file from your created package. Note over here the path, the workspace folder of your patch, then install and setup.bash, and here we are. We are ready to go. Now we need to start our launch file. To do that, we simply type ROS2 launch, then the name of the package and the name of the file, and bang. Now, first time you start RViz, nothing will be shown over here. This is really, really important to keep in mind. So do not panic if you don't see anything over here. That's perfectly normal. We need to do several adjustments, and then we need to save the configuration file such that next time we run the RViz, everything will be set properly. So let's start with modifications. Okay, first of all, click here, add, and then find over here robot model. So let's now be careful and let's find it properly. Here it is. Good. Click on OK. Now if you expand the robot model, here click on description topic and then click on robot description. And once you do that, you'll see that these links will pop up here. However, they're still not being properly placed. Now, the next thing you need to do is to set the fixed frame. This is very, very important. So here in this fixed frame option, you have map. However, here you need to specify your base link. So let's go back to the URDF file. Here it is. And then here you need to specify the frame to be the frame of the base link. So let's copy this name. Let's go to RViz, and over here let's just paste this as a base link. This is really good. Now the base link is properly displayed. However, these other links are not properly displayed. Why is that? So what's the reason for that? Well, there are several reasons. One of the main reasons is that nothing is being published. Namely, we are running two nodes. To show what the nodes are running, go back to this terminal and look what has been started. Okay, so let's see what is being started. Robot state publisher started and RViz being started. However, the robot state publisher through the topic joint states receives the joint position, and currently the joint position is not defined. That's why you're seeing this. The joints will be properly oriented once we start the joint state publisher node. Okay, before we do that, we need to save this configuration. How to do that? Well, let's go back to the launch file. And if you go back at the top of the launch file, you will see this relative path of the configuration file, and this should be the name of the configuration file. So let's copy this name. Then let's go to RViz, click on File, Save Config As, and then here is the trick. Here you're being directed not to the original folder of your package. Okay, this is very important. So go back to the demo.ws, go to the src or source, then go to demo robot, and then go to the config folder and save the file as config.rviz, save it. Okay. Now let's close RViz. The easiest way to do that is to go here and press Ctrl C. Then go back to the original terminal where you build everything and repeat the build command. So again, repeat the build command, then go back over here to this terminal, then again source everything, and then start the RViz visualization, and the RViz visualization will be loaded and you will see that all the settings will be properly configured. Good. The final step is actually to start the joint state publisher. Okay, to do that, click here, open a terminal, and inside of this terminal you need to source the environment. However, you're sourcing an overlay. That is, you're sourcing the configuration file of the created package. You need to run this, and then after that we need to run our executable file. To do that, we need to run this ROS2 run, then the name of the package, and over here is actually the name of the executable. The name of the executable is actually the name you define in your CMake file, and here it is. Test control, and this is the executable for the source file, source test.cpp. This is really, really important, and once you do that, if you press enter and something happens. So let's see what happens. Open RViz, here it is, and beautiful thing happens. You can see how our motion is being simulated, and this is really, really nice. Here it is, everything is being simulated and everything moves as expected. And now over here I'm going to resize and to show you everything, and you can see it. Okay, that's all for today, and thanks for watching.